give this talk, and I will talk about flows, but it's not the Anderson flow. It will be more like a partial hyperbolic thing. And also the manifold I'm considering is different from, like, I think most of the talks I will considering like not only non-compact manifold, but the manifold with infinite volumes. So let me first give the definition of geometric finite hyperbolic manifold. First, some examples and the Wiscast. So classical example is an example for finite volume case. So it's like SO2R, SO2Z. This kind of surface is geometric finite hyperbolic with cusp. So for higher dimension, because we will talk about free flows, it's more interesting for higher dimensional case. And for higher dimensional case, you have this kind of thing. Caution about H3. So it's the group of 2x2 matrix with coefficients in Zi. And this group should be understood as a subgroup inside here, SO2ZR. This is a subgroup inside SO2C, which is the isometric group of H3. So these are classical examples coming from the finite volume case. But here, I want to give an example of infinite volume case, which is new, like in our theorem. So first, this is up half space model for the hyperbolic 3 manifold. It's universal cover. And then you have two elements, like H. H here is just a translation. If I write down, so H is a hyperbolic element, it's just a translation. Like this. And then you have is a group generated by GH. H is the parabolic translation. And G is some hyperbolic element. Its action, it maps the inside of some, this is like half ball. It will map the inside of half ball to the outside of this other half ball.
There's some geodesic that go
some geodesic goes
inside one half ball. It's translation along there.
Yeah, exactly. Thanks for the comment. Yeah. Section like this. I call this ball like BG minus. This is BG plus. Then the action of G is like it maps G the BG minus inside the BG minus to the BG plus the complement. So it's really the expanding map. So this gives the example. So these are two elements. It will generate, due to the classical ping-pong lemma, it will generate a discrete subgroup, and then we can take the quotient. It gives us it's called a Schottky group. Some generalized Schottky group, because you have a parabolic element, and when quotient down, you get a hyperbolic 3 manifold. I can try to draw what does it like. So first, you quotient by H, then you get something like this. This is infinity. Infinity here, and then you have because this is cusp. Then when you go to the cusp, it will become very thin, and you go down, you get something very large, and then at some point you will meet this G action. So at the beginning it's just some infinite torus at each level set. Each level you have some infinite signals like this. And then when you're going down, at some point you will become still some infinite cylinder, but you have a cylinder that you have a hole. And the hole is coming from this G action. So it's some 3-dimensional manifold like this. It's a special one. can try to get a definition of geometric finite. It's something like try to generalize these kind of examples. So let gamma be a there exists a fundamental domain. Okay, d gamma. Inside this H n, which is a finite polyhedron. Here, finite polyhedron means it's a finite polyhedron, but its boundary is totally geodesic. It's like this example. I give you a fundamental domain here for this actional GH, and its boundary is just this kind of subspace or this kind of half space.
So there are 4 components to the boundary of this picture, are there?
Yeah, but the infinity is fine. Infinity.
Well, yeah, but there are the 2 vertical planes and the 2 orange hemispheres.
This is not the. This is like a fake definition. Okay, it's not the true definition. But I would like to give it a fake definition because it's easier.
Yeah. It's equivalent to the real definition, is it?
I think it's almost equal, but there are some delicate things. And for that case, we can also find some different domains. So this is this also explains that the name geometric finite because really you have some polyhedron. Then. We can talk about its geodesic flow and free flow. So if you have a finite group gamma like this, then I will call then here you will have, we'll let x is quotient manifold. Then you can have here Hn under this quotient. Then you can go to x. X is just the quotient dimension. Then here you will also have the unit tangent bundle T1H. I think in previous talk it's called S, the sphere bundle, but I like to use this notation. That if you project down, you will get the unit tangent bundle on x. Then you also have the frame bundle. Then you will get to the frame bundle. By quotient by the actional gamma, you get the frame bundle. Unit tangent bundle is just at each point you get at the unit tangent vector. For the frame bundle, you need to add the frame, and it's like you have a point here. Here is a point. Here you have a point and a vector E1, and here you need to add all the frame to x E1 to the frame is here. So this is the frame bundle, and here you have the action of the geodesic flow, GT, and here you will have the action of the frame flow, FT. The frame flow is so here it's the frame bundle go to the unit bundle. It is a principal bundle with the group is I think in this case group is SON minus 1. And the frame flow is defined you go to this stage and you take the first vector in the frame, and you can get a geodesic, and then you can do the parallel transport along this geodesic. Then this parallel transport will transfer all these frames, and you get a new frame. So this is the frame flow. And then your quotient down, you can get something on the space fx. So this is the object we will start is a frame flow, and as I said before, the frame flow it's not something really anorthogonal. It's partial hyperbolic because you have like a direction in this frame part. Come from frame part, it's a compact group which commute with this geodesic flow. So they will not the length they stays. Then. So our object is to study the exponential mixing property for this kind of frame flows. In order to study the mixing property, we need to give a good measure, a good probability measure. Because here, as you see, this manifold is far from compact. It's far from this part will have volume of infinite volume. So it's far from infinite volume thing. You cannot take the hard measure, and in this case, we will take but still there is a nature generalization. It's called the Bowen-Margulis-Sullivan measure. Let me give the definition. And in order to talk about, in order to introduce this, we first need to use Hopf vibration. So in the unit tangent boundary, you can identify it with the boundary of Hn times the boundary, and minus the diagonal part, and then plus the flow dynamic. This is like so it's easier to look at in this Pancali displays. Then for each point in the unit tangent boundary, you have base point and a direction, and then you can try to draw the infinite geodesic starting from this unit. From this in the unit tangent boundary, you get this v. Then it's a v plus. It is the geodesic go to infinity, and v minus. It's a geodesic go to minus infinity. So in a way, so by this way we get the so-called Hopf vibration, and for each point you will get v plus, v minus is 2 points on the boundary, and they will not be the same. So we need to minus the diagonal, and also there's a time part. There's still like a flow parameter for the flow. This parameter, in order to tells you like which point this the place of this vector inside this geodesic. And this will be a time parameter, and you can just fix some like reference. You can fix some reference point, and you can define this like a time parameter. So the advantage of this Hopf vibration that then, in order to construct some good measure on this space, it's enough to look at in this part. And also the flow part is already in R, so you only need to construct something on this product space. We also need to introduce the limit set. The set is actually it is you just take some point inside the manifold, and you look at its orbit, and you look at closure inside the compactified space. So you add the boundary Hn, you move the boundary Hn. You compactify it, you look at it as a ball. Then you take the intersection with the boundary. So it's like you have some orbit of this point O, gamma O, then you go to boundary, you get some fractal set. And if the gamma has finite covolume, then the limit set is a full space. And also, the other thing important is critical exponent. Which is the critical exponent of the Poincare series. Poincare series. P gamma S is equal to the sum of exponential minus S d O gamma O, where gamma is inside the group of gamma, and this d is the distance. D O gamma O is the distance in the hyperboloid. You can define delta gamma. This is a critical exponent. It is the increment or supernominal S, the real number, such that P gamma S infinite is finite. So this is the. Roughly speaking, delta gamma tells you like the exponential growth rate of the lattice point gamma. This gamma I call it lattice point. Exponential growth rate of the lattice point inside the large ball of radius t. So it's really tells it's a numerical invariant to tell you like how large the group is. Then after defining this, I can introduce the Patin-Sullivan measure. And from this measure, we can construct the Sullivan measure, which is a good measure in this setting. It is like this. It is called mu. Mu is probability measure. This measure supported on the limit set lambda gamma, such that for any element in the group, any point in this limit set lambda gamma, you have the radonic derivative. Because C is equal to the derivative of gamma at C power minus third order. Something like this. I don't remember it's plus or minus, but something like this. So if delta gamma is if the group of gamma is a lattice, then this measure mu is just the big measure on the boundary. So the radonic derivative is just the derivative. But in this fractal set, you need to make it different. And this measure is constructed by Patin-Sullivan, and it's used. I think it's used under this condition. It's quasi-invariant measure. Here, the important thing is here. It's quasi-invariant, but the next step, the nice thing is that once we put two measures together, we get some invariant measure. So then you can consider the Born-Margulis-Sullivan measure. Point V plus V minus and the T, its density will be given by the G mu V plus V mu V minus and V T. And here you need to do some correction, and the correction is given by some distance between V plus V minus and the delta. The formula is not very important, but the important thing is that after you put them together and you did multiplication, then you get this measure. The good thing of this measure is that this one is gamma invariant. And also flow invariant, just because we do nothing on the flow direction.
What is capital D?
Yes.
What is capital D?
Capital D is since like some distance on the boundary. It's more like Gromov distance, not like the Euclidean distance. Flow invariant, yes. This measure is on the universal cover. It's on the unit-tangent boundary. Then you can push down theta. Then you can get quotient. Quotient by gamma, you get some measure DMS. It is only the unit-tangent boundary of S. And you can add this M. With the flow direction. And so here it's only on the unit-tangent boundary, but what we want is on the free flow. So I will just change this here, because in fact, the Hopf vibration also works for free flow case. You just need to add the M part. So if you look at the free flow, then you will also get the same thing, but you need to multiply with this SO and minus 1. And here you will get to this M part here. And then you can add M part here. And the M part will just be the Haar measure. Some Haar measure. So then our automatic silver measure will be on the free flow. You can get the same thing on the free flow. It's also gamma invariant and flow invariant, and also M invariant on the other side. Put it here. So now I can state the main theory. Here you get a quotient measure, and this measure, and the good thing is that because we are the assumption of geometry finite ensures that this measure is a probability measure. No, it's a finite measure. After normalization, it's a finite measure, so you can be nice like a measure theoretic thing. Finite measure, and also it has maximum entropy. It's a real nice measure, and gamma is a lattice. If you are in the finite volume case, then it just gives you the Haar measure. If gamma geometry finite. At some point, it's Zariski dense. Then, in the width class. Then there is some kappa positive such that for any two observable per C and phi, which is some C1 function and the first. And you look at the correlation. The correlation decays exponentially. Phi as ft and per C. all Magritte-Sullivan measure, then DMS. Here, at the beginning, it's only finite measure, but we can renormalize it to be a probability measure. The difference is equal to some O exponential minus epsilon t, and this norm of C1 norm some norm of C and C.
Is epsilon the same as kappa?
Oh, it's kappa. Yes, thank you.
Is the risky dance necessary?
Yes. Zariski dance here means that Zariski dance. It means that in this case it means that this set gamma is not contained in subspace. In open subspace. It's like it's not contained in any like large circle. If you look at the boundary as a sphere, it's not in some like large circle.
But I think if it's contained in some subspace, then the spot of the measure will be also smaller.
Yeah, also smaller. Yeah.
But, then
like the frame, I think then you cannot go all the frame direction. There's some direction fixed. But in that case, you can just consider like a lower dimensional case.
I think here this limit set plays an important role actually because the limit set actually gives you the non-wandering set of the geodesic flow.
Yes.
Yeah.
Do you have any information on kappa?
No, but it's the method, it's Doppler's method. You not like obtain
You need a C1 in every direction.
C1, yes, C1 in every direction.
Sorry, when you say the Zariski dance with cusp, you impose that it has a cusp. Or
Yes, yeah, but the case without cusp is already done. Like without cusp. Without cusp, there are some difference. If you have no cusp, then it is called convex co-compact, and in that case, it is done by Saga-Winter. So if you don't have cusp, you are convex co-compact, and then you have like finite marker partition, finite coding. Then things somehow they are simpler. And the main difficulty is this cusp makes the non-wandering set everything non-compact, and but somehow this, but we also use this cusp to simplify the coding. Here is some, the without cusp is due to Saga-Winter, it's exponential mixing. Exponential mixing case, and also for general geometric finite, it's already studied by Flaminio and Spazzi. For frame case, Flaminio is Spazzi. And also, also Muhammad O.
What did these guys say in the general geometrically finite case?
I think they proved mixing.
Ah, but not rate. They did not prove exponential mixing.
Yeah, they have no mixing.
Right, and am I understanding correctly that with cusp means that you have finite Liouville measure?
Finite.
The without cusp case is when the regular Liouville measure is finite, and the without cusp case is when that's infinite, this measure that you're looking at is different. Is that correct?
Well, it's the same construction.
Well,
I think with cos, it's more about you have the part in the infinity.
Yeah.
Yeah.
well, there are cases in which the construction you just did simply recovers the usual.
Geometry. Yeah.
If you started with a sort of finite volume
Yeah.
thing, this construction would give you volume, wouldn't
Yeah,
it?
exactly.
And you're looking in the case where the volume is infinite,
Yeah,
and this
exactly.
does not give you volume.
Yeah.
Thanks.
Then we have a question from their method is like using representation theory. Representation theory. They look at the L2 space of S O n plus 1 S O n. They use some representation theory in this space L2. And then they can conclude with essentially this case. When the critical exponent is large. And then we have a question is that can we, because now we can prove the exponential mixing is more dynamic method. So question that why exponential mixing? Can we obtain something? Can we see something? Oh, this is representation. You see, like the representations, they should be a bit far. There, some representation cannot exist. This kind of spectral gap, but we don't know how to relate it. And from this exponential mixing, you can, like a classical, the main applications of exponential mixing is to give some speed or some counting or something. Yes.
So in the work of Mohammadi, is the rate explicit?
The rate.
The mixing rate?
Mixing rate. I don't know.
I think no, but for the geodesic flow, actually there's a paper because they use representation theory. If you work harder for geodesic flow, there's a paper by O and this Sam Edwards. So they are, yeah. So this rate is about this gap between the Laplace.
Okay. So it's more explicit than Dawkins method. Yes. And applications like error term. Error terms in counting. Like what Mark Bolico did in his first talk, he gave some exponential error term. In this case, we can also use exponential mixing. We can give exponential error term, but because in the frame flow case, we can get the equidistribution or the holonomy. Now, for each closed geodesic, you don't only have the length of the geodesic, you also have the holonomy. So you can also prove the holonomy is equidistributed exponentially. Then I will go to the proof. The proof is the strategy is classic, but there are some technical details and talks. So the first step is like coding. Coding of geodesic flow. Coding of the flow. The second step is Dirac-Piazzi algorithm. First, let me briefly talk about the coding. coding is really something which simplifies life. Because at the beginning, your flow is on a very higher dimensional thing, but the coding will reduce the dimension, and also you only need to do something about combinatories. So this coding. Coding is done in the my joint work with Wei Yu. So briefly speaking, this coding also inspired by the work of Ben Mason, Matthews Wilkinson, and we did it in higher dimensional case. So briefly speaking, let me talk about the hyperbolic upspace case. And then you have a parabolic element as before, and which fixes the infinity point. And you have something that you also have some like element G here maybe. The idea is coding is to find a Poincare section transversal to the flow. And this Poincare section is constructed. The idea is rather straightforward. So here it's the H is hyperbolic element. So you take this kind. You take an interval and you look at the unstable leaves, unstable horoscope. So it's maintaining about vectors going down. After going down, the length expands. And then we will add some unstable direction here, but that part is not that important. So, and the main idea is that then you want to going down and you want to come back to the cusp. You will go into the cusp again, you will come back. So the idea is that then you want to find some small piece like this inside. Some small piece. This small piece will go inside the manifold, and sometimes it will come back. After it come back to the cusp and go out of the cusp, it will become very long. And it will exactly be this one. So this will be the piece of the coding. And more precisely, in this picture, the coding is like, so what does it mean as this geodesic go into the cusp and go out? It just means that you will go inside some horrible. Because H infinity is a fixed point of H, but under the group action of gamma, you will have other parabolic fixed point. It's like the other lift of the cusp. So it gives you some horrible like this. This is some element of gamma maybe H infinity, something here. And this is the cusp. And your flow will going down. Then once it enters this horrible, in the quotient manifold, you will see it enter the cusp. And then you will go out of the cusp. And you go out like this small point here. If you go out of the cusp, it's in this picture, if you put it here, then it means that your flow is like this. So you go out of the cusp. And use this idea, you can try to find the small pieces inside here, such that small pieces will do this. If you go, you flow in the manifold, and and at some point you will come back and cover the full thing. So this is the coding. And just brief. So what the coding gave you? This will be a contour coding. The coding will give you, I call this just, the coding will give you some silicon G, which is open, and the merit, the Poisson merit or delta minus or delta is equal to the sum of this merit. They are open as equal. And you also for each, and there is some gamma G, there exists expanding map, which maps delta G to delta. So this expanding map is induced by this kind of return here. It will expand this piece. And moreover, because it's countable thing, you need some like tail condition. Exponential tail. Yeah, this exponential tail will make life easier. You will doing most things similar to finite coding case. Finite coding case, yeah. And then I don't have much time today. Then I'll talk about the dog-Piazza argument. So for the frame flow, the dog-Piazza argument is that you need much more accessibility things. So maybe let me borrow some notation from Zhiyan's talk. So he talked about you need to consider some trans operator, and for this frame flow case, you need to look at the curl function from this coding space delta and times some this n.
Excuse me, so is delta two-dimensional or one-dimensional?
Delta is it's this piece, so it's dimension n-1.
Yeah,
It's high dimensional thing. It's just a picture.
So you're talking about some sort of transversal to the geodesic flow and return to it.
Yes. So it's a really high dimensional thing. But for higher dimension, it's more complicated, but you still can do things similarly.
Don't you have, so you have points and also have direction? No?
Yeah.
So,
It's like in two-dimensional case, you have some rectangle, and you have directions going down. This is unstable. This is just the unstable horosphere or unstable leaf. And then this is unstable part. Then you need to add some stable part, but the stable part you don't care too much.
you only take a quotient along stable.
Yeah, you correctly take the. We only the delta is like a fundamental domain of the action of this parabolic group which fixed infinity.
Oh, I see.
Very good part in the manifold.
It's the unstable hemispherical subgroup that basically.
And the difficulty is coming from this end part. And the like. So like for the flow case, if you want to do flow-Piazza argument, so you only need to verify this so-called UNI condition, uniform non-integrability condition for just for flow case, but here it's more complicated. Here, this is some kind of accessibility condition. You will start from point X in the manifold, and then you do some unstable. You do some move on the unstable leaf, and then you do some move on the stable leaf. And then you come back with unstable and stable. And after you come back means like if you go to the unit tangent boundary, it's on the you just differ in some flow direction. But in the frame case, after you come back here, you differ like you will get something y, and x will be equal to y times this. Let me try to write it like in this homogeneous coordinate, like some at and some m part. So this is the flow part. This is the frame part. Frame part inside SOM minus 1. Then the condition, roughly speaking, that you want to do this kind of things, and you will get this kind of coming from non-integrability. You want so the geodetic case with this kind of t, but it's a rough idea. So this kind of T, they will generate a dense subgroup. Dense subgroup of R. Then it will reflect mixing. And if you can take some derivative, and the derivative of T is non-trivial, it's very rough. If you know, you know, but if you don't, I don't know how to explain. And then if you can have some derivative non-trivial, like compare different inverse branch, the derivative is non-trivial, then you will get exponential mixing. Then for the frame case, you need something more. Like for frame case, with this n part, they can like be dense in SON minus 1. Then you can get mixing. But then what about the exponential mixing case? So you still need like also to take some derivative, some sort of derivative on n part. Then this part should be. But now you are in multi-dimensional case. If you just know sum that it's non-zero, this is not enough. You need to, this kind of derivative, they can spread, they can generate the whole group. So that's something to generate a large enough group. This is still it's Pia's idea, and also it was used in Saga Winter's paper. But in our case, the difficulty comes from the fractal thing. Because this kind of unstable leaf and stable leaves, because the non-boundary set is very fractal nature. In fact, you cannot move to some point you want. You can only move inside some fractal set. So everything needs to be in the fractal. So this, and then the difficulty for this Casper case is that sometimes the limited set will very close to some like a subspace. This is the main difficulty. So only need, yes, but sometimes this limited set lambda gamma near some point, they will be inside some region like this. This is the difficulty for this geometry finite case, and with it particularly come from non-maximal Casper. And in order to, here, in order to get something like this, and in this fractal set, you need something called the non-concentration condition. Non-concentration means that you shouldn't. This kind of case is not good for that non-concentration condition. So at some point, like the point x, like near point x, you cannot get enough from the non-integrability. You cannot get enough part in this m part, so you cannot do the Doppler argument near this point. But then later we borrow the idea from Suzhi Zhang. Even though you cannot have cancellation in all the sets, but you can. But if you can do cancellation on a positive measure set, it's enough. Okay. So their idea is that if you can find some set omega inside this delta, which is a positive measure, and such that you have like large deviation property, which means that there is some kappa positive, if still positive. And for any n, and for any maybe time t, you have large deviation property. It's the measure of mu of x inside the delta, such that the time of n greater than 1, less than n, That's, if you do the expanding map, this is the expanding map T. M times this x is still in the this is less than epsilon n, which will be exponentially small. Some constant C. So in their paper, they modify a bit the dot plus argument. They only need to, only need to find some positive merit set. Here you have constellation. You can have constellation. From dot plus argument. And then what's more, this positive merit set, they satisfy this large division property. It means that if it's a merit of the set such that you don't come to this set enough often, has exponentially small merit. Combine this, you can get to the exponential mixing. So then, in our case, we need to find this set omega, and also to verify this large division property. I think briefly speaking, then what we need is we need find some good set omega, which you have some control scale and control geometry. Scale and geometry. It's like you need to rule out this kind of point, but you still can get some large set. And then you need to verify the large division property. And in this case, in order to verify large division property, we use some idea from random walks. It's called the residual waiting time. Residual waiting time for residual waiting time for some renew theory. And moreover, in order to use this residual waiting time for renew theory to get this large deviation, we need some rate of the error term. So in order to get the rate of error term, what we use is the exponential mixing of the geodesic flow. Or geodesic. So this is something we found interesting because in order to prove the exponential mixing of the frame flow, somehow you need to first prove the exponential mixing of the geodesic flow, then it gives you some technical tool to reduce things for the frame flow. So thanks, I think I finished here.
Do we have some questions?
So in the large deviation property, is it possible to make epsilon explicit?
No.
Like if I give you some explicit example, like surfaces or three-dimensional things with shorter groups.
I don't know, but maybe it's possible, but I think about it. Well, this omega, in fact, this omega you need to take a family of omega, not only one omega, like omega b. This b is a parameter from this transfer operator. Yes.
Could you replace M with any equilibrium state?
Any equilibrium state? Yeah, I think it's possible. Yeah, I think it's possible.
More questions? Okay, let's thank J.Li again. So we resume in 5 minutes.